Hey, welcome to NASA Launchpad. I'm your host, Vince Whitfield. What does a chainsaw have to do with science? Well, keep watching and you'll find out. What's one of the most important things NASA's interested in finding on places like the Moon and Mars? Let me give you a hint. You might want it on your favourite drink on a hot summer's day. But NASA has lots of other uses for it. I'm talking about ice. Not only could water ice be beneficial to the production of both water and oxygen that could aid our astronauts as they set up lunar and Martian outposts, but by studying the ice, a lot can be learned about the history of the Moon or planet. How? Well, to answer that, let's turn to HOW, the history of winter conference. And to find out how it's done here on Earth, here are Doctors Peter Wasilewski and Tony Gao to explain.
I'm sitting on a block of ice that we cut from this hole in the ice right here. First of all, we drilled a hole, augured a hole in the ice, and used this butterfly tool to determine how thick it was. And that kind of tells you mentally whether your chainsaw is long enough to cut through it, and then just how to approach it.
We were cutting blocks of ice out from the lake, mainly to look at the structure, both the bubble structure and also the structure revealed in thin sections. We used polarized light to delineate the crystal structure, crystal size, crystal orientation. Allows us to do that.
So, they're cutting the blocks to enable vertical and horizontal thin sections to be created. With these thin sections, the researchers will have a complete 3D picture of the crystal size, shape, and orientation. In addition, we'll be able to use the bubble patterns to create a picture of the rate of freezing and to correlate this with the weather record. All of this just to decipher the history of winter. Okay, so one of the things we're talking about is the bubble structure. Now, that's something that can be studied pretty easily. After all, ice is transparent, so it's just a matter of looking at where the bubbles are formed. But what does that tell us? Well, we'll let Tony explain.
Bubbles tend to concentrate during periods of fast freezing. And as the freezing slows down, they become less bubbly, the ice becomes less bubbly. And on that basis, you can distinguish what's been freezing fast, what's been freezing slow, which means what's colder and what's warmer. When it warmed up, you would get less bubbles, but when it cooled down at night, you got layers with more bubbles.
So, something as simple as bubbles can tell you all about temperature patterns. I guess in a sense, that's kind of like how you can determine precipitation patterns reflected in growth by looking at tree rings. Or by looking at layers of rock and dirt, you can figure out things like the age of the planet and the geologic history of that location. Now, something else Tony was talking about was thin sections. And what that means is basically they're taking the big blocks, slicing them down and getting them really thin, and then looking at those pieces with some nifty optical equipment. When the ice section is 1 to 2 millimeters thick, you can use polarized light to discover the size, shape and orientation of the ice crystals in the ice block. On top of a light table, you put a polarizer sheet. On top of this goes the ice section. Then on top of the ice, you put another polarizer sheet.
Light comes through the polarizer in one very narrow vibration direction. The analyzer is placed in a position where it's absolutely normal to that direction, so it doesn't let light through normally. But because ice is doubly refracting, there's an interaction between both refractive indices that produce essentially birefringence colors. And that's what you see coming out. It allows you to identify the individual crystals, which you can't do in ordinary light because it's transparent.
If you've ever worn sunglasses, you've probably used your own polarized optical filter. We all know that light has wave-like properties, one of which is vibration. Ordinary white light vibrates in many different directions, but a polarizing filter blocks out all light except the waves vibrating in a single direction. When viewed through the polarized filters, the ice crystals take on a colorful tint. This allows you to see different crystal structures in the ice that you can't see with your naked eye. The colors and patterns in the images produced using the polarized light define the type of ice and snow being studied. And because different weather conditions produce unique kinds of ice and snow, scientists can build a long-term history of the weather patterns for that area. What about other applications for this thin section stuff?
The process has been well known for a long while, at least 150 years, and has been applied to looking at thin sections of rock, for example. And now we apply it to ice, which is simply just another rock. It's a one mineral rock. In that sense, it's rather like marble. It just consists of calcite, and it's a one mineral rock.
So there you go, thin sections have already been used for several different things, and that's what science is all about. By following protocols like the ones used by the History of Winter scientists, we can take what we know and apply it to other questions. Knowing how ice crystallizes in different conditions can tell us about the temperature conditions in the lake, on the sea, when sea ice forms, etc. So whether we're carving holes in ice, looking at dirt and rock layers, or looking at all of this kind of stuff on the Moon and Mars, we've got a good idea about how we should be going about doing it. That's it for now. Thanks for watching. I'm Vince Whitfield, and I'll catch you next time on NASA Launchpad.